You are welcome to start.
All right, thank you. Thanks for the help. I'm so sorry for this. My name is Daniel Ojion. I'm a graduate research assistant from the University of Louisiana at Lafayette, and I'm here to present my research work on stabilizing sandy silt soil with fly ash-based RCA geopolymer mixtures in pavement-based layers. So as an introduction, I want us to understand that presently the soil cement stabilized base or sub-base layer that we have for our pavement is not sustainable because we have shrinkage cracks in the base layer as a result of temperature change. And also we have cracks that tend to appear as reflective cracks through our pavement layer. And in overall, these are responsible for low ride quality, water penetration to the underlying layers, which tend to affect the long-term performance of this pavement. So we also know that sandy silt soil, when subject to high saturated state, tends to collapse due to low shear resistance. And this tends to cause deformation of pavement under regular traffic. So what are we trying to do about this? So we are looking at for materials that are sustainable, which basically are industrial byproducts that can actually act as cementitious phase for this soil and also bind them together to yield greater strength than soil cement. As we also know that geopolymers in general, which these materials are called, they are long form of aluminum silicates, covalently bonded materials that are inorganic in nature. So the objectives of this research is actually to evaluate the viability of using these geopolymers, which is otherwise formed from fly ash and RCA, in stabilizing sandy silt soil. The viability we're talking about here is actually looking out for different parameters like their compressive strength, their tensile stress, and their durability in comparison to the soil cement mixtures, which is what we presently have in the industry. So the materials that we are looking at for this research, or we looked at for this research, are a sandy silt soil material sample, which was gotten from the Louisiana area. And this was tested for physical properties like the liquid limit, the plastic limit, and the plastic index. And we found the plastic index to be 7.7. We also sourced our fly ash from the Bora Resources Limited, and the recycled aggregate were gotten from a local contractor in Louisiana. And as we all know, most fly ash products are non-cementitious in nature, and as a result, they require an activation by alkaline solution to be able to form a proper binder. So the alkaline solution we're looking at from this is sodium hydroxide of 6 molarity and sodium silicate. Still under our materials and methods, we look at the elemental composition of these materials. So if you look at my screen, you see that we have different elements, but the one that is much more important to us is the aluminum and silicons, because these are the constituent of a proper geopolymer. So we look at the fly ash that we source from, and we can see that the ratio of aluminum to silicon that we have there is actually kind of encouraging, which is part of what drawn our attention to this fly ash. And the soil we're looking at also, we look at the constituent of the aluminum and silicon in the soil. We see that, yeah, it's also considerate. And we look at the RCA as well, the ratio of the aluminum to silicon. But from our overall assessment, we found that our fly ash actually had higher aluminum to silicon ratio, which is why we are also looking at this, because fly ash is actually our own target for the cementitious material, which is what we are comparing to the cement product from the control sample. Part of our prelim experiment or testing that we had our OMC and our maximum dry density. So from what we found during this testing, we found our dry unit weight to first of all increase when we increased the RCA and fly ash content by 15%, as you can see from the graph above on the screen. The first one depicts the soil only, and when we increase by 50% RCA and fly ash, both our maximum dry density increases. But interestingly, when we increase further to 25% fly ash and 25% RCA, as you can see on the screen, we have our dry density to decrease. So part of our insinuations from this was that peradventure, when we increase the fly ash content, we had, the soil ratio or the soil percentage to have decreased. And since the soil is actually denser than the fly ash, this led to the decrease in the dry unit weight. So we had our sample prepared under different testing, most importantly, the one under STM D157, which is for the compressive strength. We also have our experiment design factorial to be at different levels. So we have different, the rate under the fly ash content, we had 0%, 15%, and 25%. Under the house rate content, we had 0%, 15%, and 25%. And we also make use of a 0 silicate, 0.5 silicate, and 1 silicate ratio. A total of 13 mixtures were tested. So if we multiply 13 by 3 samples, we had a total of 39 samples in total. We had our unconfined compressive strength, indirect tensile strength, and durability test to be the overall testing that we had on each samples. Just before our result, I want to draw our attention to how we arrive at our chosen temperature of 60 degrees Celsius. So before the part of our prelim testing, we had the material tested at 25, 45, 60, and 75 degree temperature. And during this time, we found that as we increase the temperature of our oven curing, the strength, the UCS strength of the geopolymer increases. But when we got to 60 degree, we started noticing less steeper value in our slope, and we concluded that the 60 degree temperature is going to be kind of optimum for our testing. And also, in addition to that, when we compare this to the 28 degree strength of our geopolymer, we found that they are actually almost equal. And we also checked the effect of curing time on this geopolymer mixture. So what we did in this regard is we increased the duration of our curing, and we look out for the strengths that were incurred as a result of this. So when we looked at different time, which is starting from 24 hours, 12 hours, 24 hours, 48 hours, 96 hours, and we found that the strength also increased as the curing time increases. So when we finished testing using our different experiment design, we checked for the effect of the fly ash content on the UCS and the elastic modulus of our soil samples. So looking at this, the soil only, the fly ash content and the 50% fly ash, 25% fly ash. So if you look at the strength, we can see, or we can draw from this experiment or draw figure right now that there was an increase in the strength when we increased the fly ash content, and the highest increase was noticeable at 25%. Also, there was an increase in the elastic modulus as we increased the fly ash content. We also checked for the effect of RCA content, and from what we can see, for the RCA content, there was an increase in the strength up to the percentage of 15% RCA, as we can see from the figure. However, when the RCA was increased to 25%, we found that there was a decrease in strength. So what we found this to be was, we said, because knowing fully well that the soil itself has a high silicon content, if we further increase RCA up to 25%, it creates an beyond optimum requirement for the soil to actually, for the reaction to geopolymer to actually react and also yield better strength. So a 50% RCA content was found to be optimum for this reaction. So we also looked at the ratio of our silicates content and its effect on the UCS and elastic modulus. So looking at the increase in silicate content, we saw that it actually yielded a decrease in strength and a corresponding decrease in elastic modulus. So what we thought this could be was because the soil and the fly ash, when combined, they not actually requires silicate content because they already have sufficient silicate content, knowing fully well that the ratio of aluminum to silicate is what determines the strength in any geopolymer. So addition of further silicate actually does not yield considerable strength for this geopolymer. So a non-silicate content, or otherwise called zero silicate, is actually the optimum silicate, optimum value for this geopolymer. In order to determine the consistency in our test result, we actually, plotted the predicted values and the measured values of our UCS test samples, and we found a good relationship between both. And with further analysis of this, using regression analysis, we found that our optimal samples, we selected two optimal samples, which were 15% fly ash, 15% RCA, and 0% silicates. The second optimal sample that we selected was also 25% fly ash, 50% RCA, and 33% silicate. So what we did was to conduct further experiments or testing on these optimal samples and compare them to the soil cement, because what we are trying to achieve with this research is to actually create that understanding that soil geopolymer, when applied to sandy silt soil, can yield greater strength than soil cement. So when we compare this, as we can under 28 days and 7 days, we found that the strength of the geopolymers under 28 days are actually higher than the soil cement. However, the soil cement strength are higher under 7 days, because we all know that soil cement actually gain high strength fastly than geopolymer. But in the long run, geopolymer gain greater strength than soil cement. Also, we also noticed that the elastic modulus, as you can see, for the soil cement is higher than the geopolymer. This we found to be due to the fact that the geopolymer actually have a very high strength, which is a good property for them because that determines their resistance to cracking, as we'll find out later. Also, we conducted durability tests and ITS for these samples, and we found that the geopolymer mixtures actually have a very considerable durability than the soil cement. And looking at the high tiers as well, we also found that the high tiers for the geopolymers are stronger than that of the soil cement. Like I mentioned earlier, the high strain for the geopolymers actually, determines the high ITS result that we achieved there. It shows that they have a better resistance to cracking than soil cement. So these were the samples that were derived during our lab sessions. We took the pictures, and you can see that from the pictures, the soil cement samples actually shows greater cracking and shrinkage, Then we also conducted resilient and dynamic modulus for the selected geopolymer mixtures just to compare both of them. So, and we see that they both have a good value, which also showed their resistance to deformation under repeated traffic loading. And our conclusion from this experiment and this study was that if we increase the fly ash and the RCA content of our geopolymer mixtures, we have higher strength and elastic modulus. The content of 25% fly ash and RCA of 15% exhibited optimum UCS and elastic modulus. Addition of sodium silicate, as I mentioned earlier, actually created a decreasing effect on the UCS and elastic modulus of the soil RCA geopolymers. Our temperature of 60 degrees was found to be actually higher than 28 room temperature for the pure cement. Let me also point out that we actually did a 45 degree, which is the kind of uniform temperature that we usually record in Louisiana, and we found that over time, this also yielded a higher strength than the 28-day room temperature for the soil cement. So our overall conclusion is that the mechanical and durability test results show that soil RCA geopolymer mixtures for sandy sea soil exhibited better laboratory performance than soil cement mixtures. And we recommend to evaluate the actual performance of such mixtures under traffic loading and varying environment conditions. Also, further research was recommended to be conducted on the liquefaction state of these geopolymers. We thank the Transportation Consortium of South Central State, Tran-SET, for this project, and also University of Louisiana at Lafayette for this project. Thank you all for listening. Questions and answers.
Great, thank you very much. We have time for one question. If anyone has a question, we'll take first come, first serve for now. If that becomes a problem, we'll go to a hand raising method in the future. Okay, not hearing any questions. I do realize I forgot to say a couple things when I was introducing the session. First off, I forgot to introduce myself. I apologize. I came from another session and I must have forgot that I hadn't introduced myself yet on this session, but I am Susan Bogus and I am going to moderate this session. I'm on the faculty at the University of New Mexico, and we are co-hosting this conference with New Mexico State University. The other thing I do want to mention is that all of these presentations are based on written papers. All of the authors have submitted papers that are going to be published through ASCE, the American Society of Civil Engineers. So you can also access information from these presentations through those papers. And then also, if I do encourage you, if there is a subject matter that is of great importance to you or interest to you, to reach out to the authors of the paper too, and they can provide you with more information. So thank you very much. And we'll move on to our next presentation.